Okay, welcome back. Today we're going to talk about Chapter 3, Polynomial Functions, looking again at 3.4. This time we're bringing in complex zeros and the fundamental theorem of algebra. So up until this point, we've been dealing exclusively with real numbers. Today, we're going to start looking at imaginary numbers as well. So here's what we got. The imaginary number I satisfies two properties. First of all, I squared is -1. And if I have a negative number, I could pull an I out of a square root. The important part about this second property is that what I cannot do is say something like square root of 4 is equal to -2 times -2. Split these up into two square roots. Bring out an I from both of them. And turn this into -√4. That doesn't make any sense, yet each step that I've done seems logical. Well, the important thing here is that you are not allowed to do this step. You cannot split up a square root when the pieces are negative. You must first either simplify or pull out the I, and then you may split up, not before. Otherwise, you will get a false answer. I is an imaginary number, and anything that's multiplied by I is also imaginary. A complex number is a mix of A plus BI. A and B will be real numbers, and I is imaginary. It's okay for A or B to be 0, or even both of them. So for example, all real numbers are complex, and all imaginary numbers are complex. And any mix of the two is complex as well. We'll also need one more term here, complex conjugate. Complex conjugate is a new thing that we can do to imaginary numbers or to complex numbers, and it is flipping the sign on the imaginary piece. We see, for example, that A plus BI will flip to A minus BI. The symbol for complex conjugate is this bar over the Z. Let's just do a little bit of work with imaginary numbers to refresh ourselves with how they work. So looking at this first problem, 2 plus 3i times 4 plus I. I won't treat I any differently than I would a normal variable for the moment. I'll simply do some FOIL here. So I'll have 8 plus 2i plus 12i plus 3i squared. Next, I will combine my like terms. Thirdly, I squared can become a -1. And finally, I will combine like terms again. We see that very frequently we're treating I just like we would a variable, foiling it out but keeping it separate and not combining like terms. And then whenever we do see an I squared, we can deal with it. Let's skip and do the third one real fast, which comes out just the same. Notice here that 1 plus 2i and 1 minus 2i, these two are conjugates. And the point of this problem is to show us what happens when we multiply conjugates together. We'll FOIL again. 1 minus 2i plus 2i minus 4i squared. This comes out, these two middle pieces cancel entirely, and I just have 1 minus 4i squared. Now, 4i squared just becomes 4. The minus cancels. And so I end up with 5. And notice what happened here. Two things that were complex with imaginary components perfectly canceled each other out, and I was left simply with a real number. This is a trick that we can use. If we need to get rid of an imaginary number, we can use a conjugate. You may have seen this technique with square roots before. It works just the same way. We are going to apply this technique to clear the denominator in this problem. 4 plus I in the denominator is not inherently a problem, but the question asks us to write in the form of a plus bi, which means I don't want anything in my denominator. So we're going to need to fix this by multiplying by the conjugate. So I will multiply by 4 minus I in the denominator. And of course, if I'm going to do something on the bottom, I also have to do it on the top. Again, 4 minus I is chosen because it is the conjugate of the original denominator. So let's FOIL in the denominator. So I will get 16 plus 4i minus 4i cancels, so minus I squared. In the numerator, I'll get 8 minus 2i plus 3i, plus 12i, excuse me, minus 3i squared. And then I can simplify. So first, let's flip over these I squareds. So this will be 8 minus 2i plus 12i plus 3. And then the denominator is 16 plus 1. And then combining like terms, 11 plus 10i over 17. This doesn't technically fit the form that we were looking for. Normally would be okay with this, but just to take it all the way, I should split this up into two pieces, giving me 11 over 17 plus 10 over 17i. Changing things into this form can be very helpful because of the fact that I can write things with complex numbers in the denominator. Two numbers that are exactly the same may look very, very different with complex numbers. So we'll need to be able to go smoothly from one to the other. Now, tying this back in with polynomials. The goal is still to factor polynomials. And we saw last time a polynomial that we couldn't factor because the square root would have been negative if we used the quadratic formula. But now that's okay. This gives us a couple of very important theorems. Typo in this bottom piece. Let me correct that very quickly. It just means these m's need to be in the power. So first, looking at the top piece. If f is a polynomial with complex coefficients, then f has at least one complex zero. In other words, no matter what my polynomial is, as long as it's at least degree 1, so not just a constant line, but anything higher, then it does have a root. It may not be a real root, but it will have at least one root. Now, because of this, I could factor that root out. That leaves me with a polynomial of degree 1 smaller. That polynomial will also have a root, and I can continue factoring in this way until I factored everything out. Thus, this gives us a very powerful theorem. If f is a polynomial with complex coefficients and is degree at least 1, then f has n complex roots. Some of these roots may be repeated. I may just end up getting the same root n times, but I will get exactly n roots, counting the fact that they may repeat. And the polynomial will factor perfectly into a bunch of linear terms, that's just x minus the roots. Each one potentially is going to be to a power if that root is repeated. The only thing I'll have left is a coefficient out front. This theorem is huge. You can take any polynomial, factor it out, and the factorization will be unique. There's only one way to do it. This is a very powerful theorem, but it does have one major drawback. This theorem simply tells us that the roots exist and the factorization exists, but it doesn't guarantee that we'll always be able to find it. I mentioned this earlier, but for some polynomials of large degree, it is not possible to factor them. Not it's too hard, not it's impractical. Not we haven't invented a way yet. No, we have proven beyond a shadow of a doubt that there are some polynomials that we cannot find the roots. The roots are still there. There's just no possible way to find them. That being said, the knowledge that they're there is sometimes enough. We might not be able to find them exactly, but we can use graphing calculators to get good guesses at where they're at. We can use the techniques of last time to helpfully find some of the roots, and for some polynomials, we will be able to factor them completely. For this class, we're going to focus on ones that are factorable. So let's go through a couple examples. We would like to factor completely x cubed plus 6x squared plus 6x plus 5. Now, the first thing we want to do is use the rational root theorem. Nothing has changed from last time. Looking at my p's and q's, the possible choices for q are only plus or minus 1. For p, I could have plus or minus 5 and also plus or minus 1. So my possible roots are plus or minus 5 and plus or minus 1. There's not that many here, so let's just try plugging some stuff in. This time I'm going to plug into the function real fast. So if I were to take y is equal to x cubed plus 6x squared plus 6x plus 5, my calculator should be able to tell me very quickly the results for each of these 4 options. So for example, if I plug in x equals 1 here and find, let's say I call this f of x, f of 1 is equal to 18. Let's try the others. F of negative 1 comes out to be 4. Not quite there yet. Let's try negative 5. F of negative 5 comes out to be 0. That's it. That's what we were looking for. So let's stop and let's factor this out. So we'll be factoring negative 5, the coefficients 1, 6, 6, 5, and we know we should get a remainder of 0. 1 times negative 5 is minus 5, gives me a 1, times negative 5 minus 5 gives me a 1, times negative 5, but this time I get that 0 I was looking for. This leaves me with x squared plus x plus 1. Now, I'm down to a quadratic. I should try to factor. I'm not actually going to be able to factor here, so instead we'll use the quadratic formula to find the roots. X is equal to negative b plus or minus, so negative 1 plus or minus the square root of 1 squared minus 4, 1, 1, over 2 times 1. Negative 1 plus or minus root. This looks like negative 3 over 2. So this will be negative 1/2 plus or minus root 3 over 2i. So that means that x could be equal to negative 5, negative 1/2 minus root 3 over 2i, and negative 1/2 plus root 3 over 2i. And the factored form, x plus 5, x minus negative 1/2 minus root 3 over 2i, x plus, or excuse me, x minus negative 1/2 plus root 3 over 2i. A couple things to point out here before we go on to the next example. First of all, each of the factors is just like the fundamental theorem stated. It's simply x minus the roots that I got. Second thing to notice, and this one's a big one, the quadratic formula gave me a plus or minus, and that plus or minus piece included the square root, and that included the I. Every single complex root, as long as I started with real numbers, is going to arise from an application of the quadratic formula. And this means that every single time I start with real coefficients, I am going to get complex conjugates as my roots if any numbers are not real. Let's summarize that with a theorem. It's called the conjugate pairs theorem. If f is a polynomial function with z a complex 0, as long as f has real number coefficients, so no i's in the original polynomial, then the conjugate of z will also be a 0. Let's put this into practice. -1 plus 2i is a root of this behemoth. We would like to factor it completely. So the first thing I'm going to do is I'm going to factor -1 plus 2i. Synthetic division or polynomial division will still work even with complex numbers. It'll just be a little bit messy. So let's bring it down. I'll bring down 2 and then multiply. So that will be -2 plus 4i, and adding gives me 3 plus 4i. Now this multiplication starts to become messy. It's going to be a little bit of work in this next step, and that's okay. So this will end up being, let's see, first looking at the real part, that will be negative, let's just do it out on the side here. So -1 plus 2i with 3 plus 4i gives me -3 minus 4i plus 6i plus 8i squared. So that'll be -11 minus 10i will be the result. Oh, whoops, big pen. We'll do it again. So this time 13 adds with this -11 to give us 2 minus 10i. And then we'll again multiply. -1 plus 2i, 2 minus 10i. So -2 plus 10i plus 4i plus, minus 20i squared. So this becomes 18 plus 14i. Did I drop a negative somewhere? We'll find out in a moment. So adding this down, I get 25 plus 14i. We have one more set of multiplication to do. -1 plus 2i multiplied with 25 plus 14i will give me -25 minus 14i plus 50i minus 28i squared. So that will end up being 3 plus 36i. I think I did drop a negative somewhere. Because this should have given me 0 if -1 plus 2i was a root. So let's go through real fast. I'm just going to pause the recording and find my mistake very quickly. All right, so my mistake came in the middle step. This first part was correct, but in the second piece, I ended up dropping a negative, and that skewed our answer. So continuing from here, we'll next need to compute this part. So -1 plus 2i multiplied by 2 plus 2i. So -2 minus 2i plus 2i, plus 4i, excuse me. plus 4i squared. So that will end up being negative 6 minus 2i. And that will give me here 1 minus 2i. Now I'll multiply just once more. And this time, so that will give me negative 1 plus 2i minus 2i minus 4i squared. Oops, sorry, this should be a positive one here. Yeah, this is a negative one as well. That makes more sense. Okay, so then that means that I will have 5 giving me, as expected, that remainder of 0. As you can see, there's a good opportunity to make mistakes, so you'll definitely need to go slow if the problem is as long as messy as this one. That being said, we get down to our intermediary step, giving us the polynomial that we've factored so far. So I've got x minus 1, negative 1 plus 2i times 2x cubed plus 3 plus 4i x plus 2 plus 2i, or excuse me, x squared, 2 plus 2i x plus negative 1 minus 2i. Now, it would normally be very difficult for us to guess at what a rational 0 or what any 0 might be of this. But there is an upside here. And the upside is that, very fortunately, we do not have to worry about, oops, sorry about that. We do not have to worry about guessing at the answer because of the complex pairs theorem. I know immediately what my next thing to factor is going to be. It's going to be negative 1 minus 2i is definitely going to be my next choice. Because if the original one was a factor, so too should this be. So let's bring it down. Multiplying here, that'll end up being negative 2 minus 4i. That gives me 3 minus 2 is going to be 1. So then I will have negative 1 minus 2i. That will give me a 1. And then so negative 1 minus 2i gave me that 0 that I expected. And look what happened. This will happen every time you started with real numbers and factor out a conjugate. You've got a really, really ugly, messy middle step, but the next step is oh so clean. That's the whole point, is that you need a pair of conjugates. One of them's messy, but the pair of them were not messy. Otherwise, there would have been i's in the final answer, so they cancel each other out over time. This means that now I've got another factored form. X minus negative 1 plus 2i, x minus negative 1 minus 2i, multiplied by 2x squared plus x plus 1. Factoring this last piece is just a simple application of quadratic formula. Negative 1 plus or minus root 1 squared minus 4 times 2 times 1, all over 4. Thus, I get my final answer. Let's just clean this up. So negative 1/4 plus or minus, this looks like it's going to be 7, root 7 over 4i. And so my final factored form is going to be x minus negative 1 plus 2i, x minus negative 1 minus 2i, x minus negative 1/4 plus root 7 over 4i times x minus negative 1/4 minus root 7 over 4i. The roots are negative 1 plus 2i, negative 1 minus 2i, negative 1/4 plus root 7 over 4i, negative 1/4 minus root 7 over 4i. And there we go, completely factored. That's all we've got for this time. See you guys next time.